I'd like to thank the organizers for the invitation to speak here. It's a great opportunity. Although I guess I'm a bit of an interloper at a topology conference. I'm going to be speaking mostly about sort of geometric topics. So this first talk will be a survey on volumes of hyperbolic three-dimensional manifolds and overfolds. Well, the title said manifolds, but I realized I was going to talk about overfolds as well. So we'll first start in 2 dimensions. So 2-dimensional hyperbolic space can be modeled by the upper half plane. So there's a Riemannian metric, which is the standard Euclidean metric, but scaled at height y by a factor of 1 over y squared. So if we look at points and look at tangent vectors in the tangent space, the Riemannian metric is telling you how long a vector is. So all of these vectors here will have equal size. So the size is scaled by 1 over the height. And in this metric, the geodesics will be either vertical lines, so lines orthogonal to the boundary of hyperbolic space, or there will be circles which are orthogonal to the boundary. And the group of isometries of hyperbolic space is equal to PGL2R, so the projective linear group. So this acts on, we can think of the upper half space as, we can think of it taking C minus the real axis and mod out by complex conjugation. And then the action of PGL2R is by fractional linear transformations. So if I have a complex number, then it's taken by this 2x2 matrix to AZ plus B over CZ plus D. Generally, so I shouldn't have written the determinant's equal to 1 here, just the determinant's non-zero. And if you take the matrices with the determinant 1, you get the orientation preserving isometries PSL2R. But when you have a matrix with negative determinant, then it acts flipping the top to the bottom, but the conjugation sends you back here, but it'll reverse orientation. So PGL2R gives you the full set of isometries. So some of the isometries in this case are given by, well, there's a reflection through geodesic line here. So if I reflect through this line here, what it does is if this is the origin, it'll send a point z at distance absolute value z to the origin, and it'll send it so that its distance is 1 over the absolute value z, which you can write as an equation of 1 over z bar. So this, then you can write it as an equation as z divided by absolute value z squared. So that's an inversion. That's an inversion through this line, or actually on the complex plane, it'll act as an inversion through this full circle. So that's a reflection, and then this is an example of a translation along a geodesic. So a translation, well, I'm thinking here now the origin is here. If I take this matrix, well, square root of A and 1 over square root of A, this is one with determinant 1, it's orientation preserving. Then this translates, well, it'll take Z to AZ. This is a translation, well, this is multiplication by A, but in the hyperbolic metric that corresponds to translation by the natural logarithm of A. So if you integrate the lengths of vectors from here to here, the integral of 1 over y from here to here will just give you the natural log of the ratio. And the ratio between AZ and Z is just A. So natural log of A is this distance here. Okay, so those are a couple of examples of hyperbolic isometries. So what we'll be interested in this talk is discrete subgroups of hyperbolic isometries. So if gamma in PSL2R is a discrete subgroup, then, so this is just discrete in the natural topology on PSL2R, topologized as a group of matrices. Then H2, if we mod out by the action of gamma, this will be a two-dimensional orientable hyperbolic orbifold. If we allow subgroups of PGL2, then we'll get non-orientable ones as well. So the classic example of this is PSL2Z, and a fundamental domain for this action is given by this region here. It's bounded by two lines and two circles here of radius 1, centered at 0 and 1. So the group is generated by, well, we have a translation here by 1 given by this matrix, and these two sides, so we can think of this as a quadrilateral with, there's a vertex off at infinity, which is called an ideal point. And these two sides of this polygon are glued together by this transformation here. There's also rotations about these vertices here. So when you mod out by this group action, what happens is the group acts mostly free, but there'll be some fixed points at these points, and there translates into the group. There's a rotation of order pi here, so an involution fixing either of these points. These 2 points get identified, so they correspond to the same point in the quotient. And this point here, there's a rotation of order 2 pi over 3. So you get these cone points in the quotient, and the quotient looks something like this. So you have this cone point of order 2, a cone point of order 3, and then you have this infinitely long thing that gets skinnier and skinnier as you go off to infinity. So as you go up to infinity in the upper half plane, distances get closer and closer because they're scaling by 1 over y. And so this thing gets exponentially thin as you go off to infinity. So this goes off to infinity. And you can think of this as a cone, like a cone point of order infinity is the natural interpretation here. So this translation here is called a parabolic translation, and these rotations are called elliptic elements. So when you take this fundamental domain and you act by this group, or rather PGL2Z, you'll see some picture like this. So the images of all these translates. So the fundamental domain for the action of PGL2Z, once you add in reflection corresponding to complex conjugation here, then the fundamental domain will be half of the fundamental domain of the orientable group, and you'll get just this this triangle here with one vertex off at infinity. And so if you look at the images of this fundamental domain, they'll tile the hyperbolic plane. The area of this orbifold is pi over 3 in this case. Now, orientable orbifolds are determined by the number of one handles, so the genus. So one handle you can think of as just a little 2 torus that's been connect-summed with the surface, and the number of cone points of each order. So if we have a cone point of order 2 pi over n, then locally it will look like you've taken a wedge of paper and you've glued two sides of it together, and you get this cone point there. So for example, H2 mod PSL2Z has cone points of order 2, 3, and infinity. Now if you consider non-orientable orbifolds, there's a similar classification. I just didn't want to get into that. But there's a similar classification in terms of a few extra bits of data. So to compute the area from this data, you can use the Gauss-Bonnet formula. If S is a two-dimensional hyperbolic orbifold, then the area of S is equal to minus 2 pi times the Euler characteristic. So the Euler characteristic here is the orbifold Euler characteristic. Well, the orbifold Euler characteristic is multiplicative when you take covers. So you can imagine just taking a finite index cover of the orbifold. So you can take a finite index subgroup which doesn't have any torsion, and then you'll get a surface. You take the Euler characteristic of that, and you divide by the index of the cover. So that's one way to get the orbifold Euler characteristic. But you can compute it directly from this data via the formula. So you have 2 minus 2g, the usual formula for Euler characteristic, but then the cone points contribute 1 minus 1 over mi, where mi is the order of the ith cone point. So and if mi here happens to be infinity, like in the case of PSL2z, then of course you'll just get 0 here. So you just get the 1. Now you can get a fairly direct proof of this by cutting up your surface into triangles and then using this formula for the area of a hyperbolic triangle. So if I have a triangle in the hyperbolic plane with corners of angles alpha, beta, and gamma, well, this is non-Euclidean geometry, so the sum of these angles is less than pi. And the area then is pi minus alpha plus beta plus gamma. So you can then deduce this Gauss-Bonnet formula very easily from this formula for the area of a triangle. So or you can think of this as a special case of this formula if you allow angles which are not just rational submultiples of 2 pi. Okay, so unfortunately in 3 dimensions, this Gauss-Bonnet formula, there's no really nice analog of the Gauss-Bonnet formula. Well, there's some analogs, but they're somewhat complicated. Here I did the computation for PSL2z. So it has these 3 cone points of order 2, 3, and infinity, and the Euler characteristic is minus 1/6 then, and the area then is pi over 3. So it's easy to see from this formula then that if you could look at the collection of all areas of 2-dimensional hyperbolic orbifolds, then this is a subset of the real line, and it's a well-ordered subset. And the ordinal type is omega to the omega. So, and for a given area, there's only finitely many orbifolds that have that area. You can have multiple orbifolds which have the same area, but there's only finitely many. Finitely many orbifold types I'm saying here because you can have different orbifolds up to isometry which have the same set of collection of cone points or genus. So that's Teichmuller theory, which I'm not going to worry about. Now n-fold limit points of area, these correspond to an ordinal of the type using ordinal arithmetic alpha plus omega to the n. So if you look at the tail end, it looks like omega to the n. These correspond to orbifolds with n cone points of order infinity. So these are punctures or cusps. So geometers call them cusps. These are parabolic points if you think about it like a Riemann surface. So the order of the limit point corresponds to the number of cusps. And again, I'm thinking just about the orientable case for simplicity, but there's an analog in the non-orientable case. So here's a picture of the spectrum of areas of 2-dimensional orbifolds. So the smallest area is this 2, 3, 7 orbifold. So you take a triangle with corner angles pi over 2, pi over 3, and pi over 7, then you double it and you get this orbifold of area pi over 21. And so then you can take this highest order cone point and start bumping up the order of the cone point there, decreasing the angle, and in the limit you'll limit to a puncture, so a cone point of order infinity here, and the area is pi over 3. So this corresponds to PSL2z. Now this happens to have the same area as a compact orbifold, this 2, 2, 2, 3 orbifold. This is the first limit point, but there's also, it matches with this the area of this compact overfold here. Now the second limit point then is this 2, 4 infinity overfold of area pi over 2. And then we have 2, 5 infinity, 2, 6 infinity, 2, 7 infinity. So these correspond to, so if we're counting ordinals, so this is the first ordinal. The cardinality, of course, is just z. And then we have omega plus 1, omega plus 2, all the way up to 2 omega, and et cetera. So then you do 2 omega plus 1, 2 omega plus 2, et cetera, up to 3 omega. So the ordinal type of these ordinals is all ordinal type omega, because you can write it as a sum of the ordinal plus omega, omega plus omega, or 2 omega plus omega. Now the first accumulation point of accumulation points then is of ordinal type omega squared, and this you see 2 cusps here. So we have the 2 infinity infinity orbifold, and now there's two of these order infinity cone points, and basically it's a double limit point because you can either make this one finite or this one finite, or of various orders, and you get these various points which accumulate onto here as the two numbers go to infinity. So there's two sort of numbers you can play with here, which is why it's of order omega squared. And this also happens to have the same area as a torus with a single cone point of order 2. So this is genus 1 with one cone point of order 2. Okay, so this is the spectrum of areas of two-dimensional hyperbolic orbifolds. And here the areas are, they're all rational multiples of pi, of course, because of the Gauss-Bonnet formula, and things are fairly nice. So now I want to go on to talk about the three-dimensional case. Is there any questions so far? Hopefully it's a review for a lot of people here, but yes, question? Yeah.
What are the possible reachables of integers, I guess, that you can have as, or just sets of integers that you can have as the cone points?
Oh, yeah, that's a good question. So the sets of cone points that you can have, and basically it's arbitrary. You just restricted, the Euler characteristic has to be negative if you want to get a hyperbolic overfold. And there's only finitely many, there's infinitely many spherical or Euclidean examples, but there's essentially a small class of those. That's why, if you started with 2, 3, 6, the Euler characteristic would be 0, and you would be here, but it's not really a hyperbolic overfold. That's why it starts here at pi over 21. Yeah, that's a good question. Okay, so now in the three-dimensional case, we have a negatively curved Riemannian 3 manifold of constant sectional curvature -1. Well, if you're not familiar with Riemannian geometry, I'm not really going to go into explaining what that means, but there's a physical model that you can think of taking a laboratory experiment where you create a piece of glass where the index of refraction varies as 1 over the height above the table. So you have this glass sitting on this table, and or another way of saying it, so the speed of light and the index of refraction are inversely proportional, and so the speed of light will be proportional to the height above the table. So the geodesics then in this, so you can think of this as a metric where 2 points, the distance between them is the amount of time it takes for light to get from one point to the other along the shortest path. And well, if you were to shoot a laser through this thing, the light would take a path that follows a circular arc that's orthogonal to the tabletop. Or, well, you can imagine the circle getting larger and larger, and as one point goes off to infinity, you'll see a vertical line. So either a vertical line or a circle that's orthogonal to the tabletop. And there's also these totally geodesic planes, then, which are hemispheres that are orthogonal to the tabletop. And these are actually a copy of, isometric to a copy of hyperbolic two-dimensional space. So you can imagine also a vertical plane in the limit. When this radius goes to infinity, you'll get a vertical plane, which is also a copy of hyperbolic 2 space, where the metric varies as 1 over the height above the table. Now you can imagine why this, if you had 2 points here, and you want to get from one to the other, if you go straight through, it's going to take longer than going up, where it's sort of easier to move, and then coming back down again. So that's sort of roughly why light will follow a geodesic that goes up where it can move quicker and then come back down again. But once you're going vertically, because of the symmetry of the situation, you remain going vertical. And as light gets closer and closer to the surface of the table, it'll be moving slower and slower. The speed approaches 0, and so it'll actually never reach the tabletop. It'll take infinitely long, so the tabletop's infinitely far away.
You seem to have a preference for upper half-space models.
Right.
Is there any reason for that?
Yeah, the upper half-space model is just easy to describe. That's all.
But it distinguishes infinity, which always bothers me.
Yeah, that's right. It's well, I'll have some pictures later, which aren't the upper half-space model, but yeah, there's other models, the Klein model, Lorentz model, and various other. Each model is sort of useful in give you a different perspective on it, but none of them are actually completely accurate because they're distorting. Obviously, this is a straight line, but to us it looks curved. So with Euclidean eyes, things aren't quite right. You can actually draw things in correct hyperbolic perspective, which is what there's a program called GeoMView that does this. But anyways, this is a model that's easy to describe. And if you actually wanted to create some glass like this in a laboratory, I think this would probably be the easiest model to work with, because you just have these layers where you'd have to change the index of refraction, sort of just like would be constant on each layer. So I've asked physicists to try to do this, but no one's taken it. In principle, it would be possible just by doping. You take some glass and you would dope it with various sorts of molecules to make the speed of light change. And this is actually what they do in fiber optics cables. They dope the silica so that the speed of light changes when you come to the boundary, and so the light rays get refracted back in, or sort of curved back in rather than bounce back and forth. And this keeps the packets of light closer together so that the light's traveling along similar paths. And so that's actually how when I read about these fiber optics cables, that's when I thought about these hyperbolic glass. So in principle, it would be possible. So you could, if you had a chunk of this hyperbolic glass, you could cut out some tetrahedron here. Well, I've just drawn a 2-dimensional version, and you just silver the sides. I guess you'd have to cut out a little peephole, but you'd look in and you'd see this 3-dimensional hyperbolic kaleidoscope. So it'd be cool if someone could actually make this. But, probably not a very good investment of NSF money, though. So in the 3-dimensional case, there's well, the 3-dimensional version of these triangles or tetrahedra. So here's a picture of an infinite tetrahedra. It goes off to infinity. There's 4 sides to this. There's 3 vertical sides, which correspond to a 2, 3, 6 triangle. And then there's a geodesic plane here bounding the 4th side. And I've drawn the dihedral angles of each of these things. Now the hyperbolic space is it's a conformal model. So this upper half space model is a conformal model. So angles here in the hyperbolic plane are the same as Euclidean angles. So the actual Euclidean angles here will be the same as in hyperbolic space, and they're Riemannian metric on hyperbolic space. So here we see, going off to infinity, we see this 2, 3, 6 triangle, which gets exponentially thin. So this is analogous to a cone point in the 2-dimensional case of order infinity. And here then we have this other side, which is finite. Now it turns out this corresponds to the group PGL2 Z adjoin the cube root of unity here, which is the group. It's the ring of integers in the number field Z adjoin square root of -3. Well, we have to adjoin reflections to get these vertical reflection sides. This is actually, you would take this tetrahedron and you would double it along its boundary to get this one, because this is actually an orientation preserving group of isometries here. And then the second one is PGL2 Z adjoin I. These are called Bianchi groups. And I guess I got maybe things out of order here. Right, so the identification here with these groups comes from the isometries of hyperbolic 3 space being, at least the orientation preserving isometries are PGL2C. So here we take PGL2C as GL2C and you mod out by the center, which are the diagonal, which are the matrices that are multiples of identity. One way of, oh, this thing got messed up here. So the quaternions, this is a classical Hamiltonian quaternions, is a 4-dimensional division algebra. So we have A, B, C, D in real numbers, and then we have it's spanned by I, J, and K, and 1 satisfying these formulas here. So this is the unique 4-dimensional algebra, division algebra defined over R. And we can define an upper half space as a 3-dimensional subspace here spanned by 1, I, and J, so that C, the third coordinate of J, is greater than 0. And then if I have a matrix in SL2C, so the determinant is 1, then you get an action on, so it's analogous to fractional linear transformations, you get an action that preserves this upper half space. But here we need the determinant of the matrices to be 1 to get this action to work out correctly. So this extends the action of GL2C by fractional linear transformations on the projective, complex projective space. So the action this action here, if I plug in, if I forget about this coordinate here, so if I take coordinates on the tabletop, which is just the complex plane, then this is just the usual fractional linear transformation acting on the complex plane, or rather the complex projected plane, because there's infinity as well when you consider this action. So this is the complex projected plane. Then is just a sphere bounding hyperbolic space. So like Bob says, you can't really see this in the upper half space model, but there's a ball model of hyperbolic space where you see that clearly. Now this extends to an action at GL2C where you just take a matrix and you divide it by its square root of the determinant to get 1 with determinant 1, and then you get this action here. And conjugation of C corresponds to a reflection acting on upper half space. And then you can add that into your group and you get the full group of isometries of hyperbolic 3 space. So it's convenient to work with GL2 because, so here I'm saying PGL2 of this ring of integers, these are 2 by 2 matrices, but actually when I say GL2 here, I want the determinant to be an invertible element of the ring of integers here. So this is sort of a different meaning of PGL2 here. But then you get this action via this formula here. Okay, well, so I gave a couple examples of hyperbolic lattices. So how do you compute the volume? Well, one way of doing it is you can first compute it for tetrahedra. So the volume of a tetrahedron with all its vertices at infinity, these tetrahedra are parameterized by a Euclidean triangle with angles alpha, beta, and gamma. Alpha plus beta plus gamma equals pi. And the volume is equal to the sum of Lobachevsky function of alpha, beta, and gamma. Here's the formula for the Lobachevsky function. And this formula basically comes out of integrating in the upper half space. You just integrate the volume form, 1 over y cubed, over a region. And actually, the way that it splits into these 3 parts can be seen geometrically via, well, we can stick a circle, a geodesic plane that's the boundary, a circle that's the boundary of this geodesic plane here, and we see this triangle inscribed inside of there with corners alpha, beta, and gamma. And the formula here comes from, you basically look at the center of this circle, and you can split up your tetrahedron into simpler tetrahedra, which depend only on the angles alpha, beta, and gamma. And so this formula actually comes from the geometry as well. Now, when alpha, beta, and gamma are all pi over 3, your tetrahedron is completely symmetric. It's regular. The volume then of this tetrahedron is maximized. The volume I'll call V naught here is, well, it's 3 times the Lobachevsky function of pi over 3 is 1.01494. It's some number. It's unknown whether this number is rational or irrational. It's clearly transcendental, but no one knows how to prove it. Now, when alpha and beta are pi over 4, then I'll call this number V1, the volume there, 0.915 something. Some people call this K, Catalan's constant. And as a formula here, you take the alternating sum of 1 over odd numbers squared. And this comes out of some number theoretic formulas. There's also a nice number theoretic formula for this. It's values of certain L functions. Certain zeta functions associated with number fields. But anyways, this is the volume of this tetrahedron with the right isosceles triangle. So the volume of H3 mod PGL201, this is the Z adjoint I one. This is Catalan's constant divided by 6. And PGL203, you have V naught divided by 12. So these formulas are due to Humbert. So you can compute there's formulas for, this is a formula in the ideal case, which is much simpler to write down. There's formulas obviously in the case of finite tetrahedra as well. And you can get formulas for volumes of Overfolds by cutting the Overfold up into tetrahedra and summing the various volumes of the tetrahedra. So now I want to give some examples, some other examples of three-dimensional hyperbolic orbifolds and manifolds. One of the oldest hyperbolic manifolds to be discovered was the Giza King manifold, which is obtained from the regular ideal tetrahedron with dihedral angles pi over 3 by identifying the faces in pairs. And so here's a picture of it. So if you orient the edges this way, there's a unique way actually to identify the faces in pairs so that the orientations of the edges match up. So here, this face G gets identified with this face here, and the back two faces get identified in this way. And you can see that it preserves the orientations of the edges there. So you can just do this purely topologically. If you do this as a topological space, you get a tetrahedron, and the vertex will have a link, will be a Klein bottle. So actually I want to remove that vertex, and I'm going to think of that as being off at infinity. So when I identify these things isometrically, I get a cusp that's homeomorphic to a Klein model across with 0 infinity. So, you can also see that when you glue these faces together, so the ideal triangles in hyperbolic 2 space, there's only one up to isometry. So PSL2 acts transitively, or PGL2 acts transitively on triples of points, which correspond to ideal triangles. And so there's one way to glue the faces together isometrically, and then all the edges will get glued together. There's 6 edges here with dihedral angles pi/3, and they'll get glued together cyclically to get the angles they'll be flush in the end, and you get an angle of 2 pi around that edge. So you actually get a hyperbolic metric on this space. Yeah, question? Yeah.
Boundary?
What's that?
But why is there boundary?
So when you glue a compact tetrahedron together, there'll be no boundary, but the vertex will be singular. It won't be a manifold point. So you remove that manifold point, and then you get, it's not really a boundary, but it's a cusp. It goes off to infinity. You have this Klein model that gets exponentially small as you go out the cusp. So,
but on the homeomorphism, there's boundary.
Here, right, sorry. I'm chopping this off at one point and then looking at the end of the manifold. So this is the end of the manifold, sorry. This is the boundary, the frontier of the end. Yeah, thanks. Okay, so this is just a neighborhood of the vertex. Okay, does that make sense? Okay, so
Is there a choice about how you glue the edges?
oh, yeah, well you can try, you just take a tetrahedron and you can glue the edges, or glue the faces together in all permutations. So people have done this, and this turns out to give you a manifold. If other ways.
In terms of sliding.
Oh, yeah, okay, yeah, so that's a good question. So any 2 edges are isometric by isometries, but the faces, it turns out, there's a unique way to glue them together. So there are examples where you could try to glue things together cyclically, but then things get shifted as you try to match them up, and you don't actually get a hyperbolic structure here. But because of the symmetry of the situation, that doesn't happen. Right. So, but the faces are unique. They're a unique way of gluing them together, and that determines how the edges are glued together isometrically. Yeah, that's a good question. So I'm sort of, there's a lot of details behind this, but I'm sort of just giving you just an outline. So. But this is a special case of the Poincare polyhedron theorem. Now you can get some other manifolds in a similar way. So if I take 2 of these regular ideal tetrahedra and I glue the faces together in this fashion, there's a unique way to glue these together. So you glue every face here to a face here with the corresponding orientations and colorings. And it turns out when you do this, you get the figure-8 knot complement. So this was discovered by Bob Riley in the 70s, and then Bill Thurston discovered it independently. And you can actually see these 2 tetrahedra in the knot complement. If you're Bill Thurston, anyways, you can see them. But there's an orientation reversing involution. So figure-8 knot lies inside of S3, and you can take the you can think of that as a suspension of S2. You can take the orientation reversing involution on S2 and suspend that. So you're going to have 2 fixed points which acts orientation reversing, and there's 2 points in this knot you can make it so it's symmetric with respect to this involution. And the quotient manifold, so the quotient of S3 will be RP2, a suspension of RP2, which has these 2 sort of cone points. But if they lie in the knot here, the quotient, it gives you a manifold because you're taking the complement of the knot. And the manifold you get is the Giza King manifold. So this picture here actually double covers this one. There's a similar example that's called the figure-8 sibling. It's not a knot complement. But it's also obtained from these 2 tetrahedra by gluing them together. And the dihedral angles, there's 6 purple edges, 6 orange edges, so the dihedral angles all up to 2 pi there, and you get a nice manifold. And these are all subgroups of PSL203, one of the examples I had up earlier. So similar to the two-dimensional case, the hyperbolic 3 overfold is just a discrete subgroup of isometries of H3 modulo the group gamma. So this is overfold O. There's a way to describe this more intrinsically in terms of topological space, and there's certain, every point has a neighborhood which is modeled on Euclidean space modulo a finite group, and you keep track of the point stabilizers. Now, a nice example of orbifolds is if you take a polyhedron that has dihedral angles of the form pi over k, where k can be 1 or it could go off to infinity, then you obtain an orbifold just by putting mirrors on the faces. So what I mean by that is on each face you think of it as it's not really an orbifold it's not really a manifold with the boundary of the polyhedron. Really, the faces correspond to fixed points of a reflection in hyperbolic space. So here's some tetrahedra. So here's a tetrahedron. I've written here the sub-multiples of pi that the dihedral angles are. So there's pi over 3, pi over 5, pi over 3, and then 2, 2, 2. These are called orthoschemes. And this guy, there's a symmetry when you rotate like that, and I can take the quotient by that, and I get this orbifold here. I'm actually doubling it along the boundary to get something orientable rather than mirroring the faces. And then you see this. So you have this graph in the 3-sphere, but metrically you have hyperbolic metric outside of here, and then along these singular locus, it looks locally like H3 modulo this finite group of rotations. And around the vertices, you see H3 modulo a finite point group, like rotations here of 2, 3, 5. That's the rotation group preserving an icosahedron or a dodecahedron, for example. And the volume of this is 0.03905. Here's some other examples of reflection tetrahedra with various volumes, 0.0718, 0.0933. There's only finally many of these reflection groups in tetrahedra, it turns out, in 3 dimensions. And the original 2 examples I had up were also these reflection groups in tetrahedron with the vertex off at infinity, which I've drawn with a little circle here. So these are non-compact. These go off to infinity here. Okay, well. So a bit of topology. If we have a 3 orbifold with torus boundary, we can take this, so for example, we can take the trefoil knot complement. So if I take the trefoil knot, I remove a little neighborhood of it from S3, I get a manifold with boundary. The boundary is just a torus, and I can glue in a solid torus into there differently. So if I glue it back in the way it was, I'll get back S3, but I can glue it back in so that the boundary of a meridian of the solid torus gets glued to a different curve rather than the meridian of the knot here. So like I could choose this curve that goes around like this and glue that in, and that uniquely determines how the 2 are glued together up to isotopy. So this is called a Dayton filling, and it's a way of creating 3 manifolds from knots or link complements, or more generally just from manifolds with torus boundary. Now a curve, you can specify this Dayton filling by a slope. So this is a rational number, or it could be infinite, so it's actually in PQ1. It's given by a ratio of P over Q, where if we take a basis for the homology of the torus with a meridian and a longitude, so the meridian would be the circle going around here, and a longitude would be a circle going all the way around, which bounds a Seifert surface for the knot. So you can uniquely determine mu and lambda if you have a knot complement, for example. Then P over Q is just the ratio of the coefficients here. So this gives you a natural identification with Q union infinity. And when you have an embedded curve, these 2 numbers have to be co-prime. If it was a multiple, then you'd be winding around the same curve a number of times. So that's why the ratio is all that matters. So here I have a picture of a torus with meridian and longitude, and I can cut it open and see this picture here. So the meridian has slope infinity because it's corresponds to 1, 0. The longitude has slope 0, corresponds to 0, 1. And this curve here has slope minus 1, where you have coefficients minus 1 and 1, say. So that's how you parameterize a Dane filling. Now here's a picture of the Whitehead link. The Whitehead link has a hyperbolic structure where you take an all-right ideal octahedron, and here's the upper half-space picture. So here's a picture of an octahedron. It has 6 vertices. There's one off in infinity and these 5 here. And you have these 4 vertical faces and these 4 geodesic hemisphere faces. You can actually see this. So this is, if you can really understand this picture, I mean, not off the top of it, but if you can understand this eventually, that's sort of the, the crucible for whether you can be a 3-manifold topologist, if you can understand pictures like this, I guess. But anyways, you take an octahedron, and you have these, you can take the alternate faces. So there's these 2 red faces on top, and I fold them together like this. And here, these vertices are removed. These are off at infinity, so they don't actually exist there. And I take these bottom 2 faces like this and fold them around. And what you see is something like this. So these brown vertices get glued together to form this ring here. And these green vertices get, when you get folded together, you see these 2, so these things are actually drilled out. The vertices don't exist there, so you can sort of stretch them out, and you get this picture here. You see the red triangles glued together and the blue triangles glued together. And then I can glue the top to the bottom here. This brown guy gets glued around to form a torus, and I see the complement of the Whitehead link here. So these 2 green tangles here get glued around to form this Whitehead link here. And you can see that these gluings, again, the triangles get glued together uniquely isometrically, and you get this hyperbolic metric because you have 4 dihedral angles adding up to 2 pi around every edge. So if you just check the combinatorics, so there's 4 faces getting glued around every edge. So that's the hyperbolic structure on the Whitehead link complement. Now I can do Dane filling on the 2, so I can think of this as, well, these vertices are off at infinity, or I can sort of chop them off and I get a manifold with torus boundary, which I can do Dane filling on. And if I do the -5 halves, -5 filling, I get a manifold which is called the Weeks-Matveyev-Fomenko manifold. It was discovered independently by Weeks and Matveyev and Fomenko, which has volume 0.9427 something. I mean, this continues on. There's another example discovered by Meyerhoff that has this volume here. Now these, you can compute these using a program called SnapP, developed by Jeff Weeks, which is how he discovered this manifold. Now Mostar rigidity says that if I have 2 groups, which are subgroups of Hn, Hn mod gamma I has finite volume, and they're isomorphic to each other abstractly as groups, then the 2 corresponding orbifolds will be isometric to each other. This is only for n greater than 2. In dimension 2, this fails. So therefore, the hyperbolic volume is a topological invariant. So if I have a knot or link complement that has a hyperbolic metric, that volume gives me a topological invariant. And it turns out it's a good replacement for the Gauss-Bonnet theorem in 3 dimensions. All right. I only have 10 minutes left. All right. Now, Margolis's lemma tells you something about the structure of these hyperbolic orbifolds. So there's a universal constant epsilon, so that if I take a geodesic of length less than epsilon in a hyperbolic 3 orbifold, then it has a tubular neighborhood of large radius depending on that epsilon. So another way of saying this is that if I have x in H3, or this works in Hn in general, and I take a discrete subgroup, then I look at all the, I look at the subgroup that translates a point x in hyperbolic space by less than epsilon, then there's an epsilon so that this G always has to be elementary. So it either is a finite group or it's virtually abelian. It's virtually translation along a geodesic or a parabolic group fixing a cusp. So, so if you have so in the polyhedron case, it's sort of easiest to see that if I have a very short edge of a polyhedron, then so say it has a very large cone angle here, n, then there's going to be a large tube around it embedded in this polyhedron where you don't see anything else happening. There's no vertices or anything else inside here. It's just a nice collar neighborhood of that. These edges, dihedral angles, will have to be pi over 2, it turns out, because the group has to fix this geodesic in hyperbolic space. Well, you can't really see it, but if this was a very short geodesic, I can't really draw it, but then this will have a large tube around it. And this looks locally like H3 modulo a translation and rotation along a geodesic. And then we have, we can take two parabolic elements acting by Euclidean translations on the upper half space model. And this is what you can see around a non-compact, so near like one of these tori in the wide link complement. You'll see a picture like this. It looks like a torus that grows exponentially thin as you go out the end.
What's the role of R in that term?
Oh, the role of R is, so there's some R depending on epsilon. There's an epsilon, there's an R depending on epsilon, so that if epsilon, if you have a geodesic length epsilon, then there's a two-body neighborhood of radius R about that. So I haven't stated this very precisely. This is a little bit more precise statement. But from this, it turns out that if you choose epsilon smaller and smaller, the R will get larger and larger. So you have, so the very thin parts of the manifold, where the injectivity radius is small, will be will look like these very large tubes around short geodesics. I haven't been too precise with how I stated it here, but there's it follows, well, there's a much more general version of this that holds in asymmetric space. Okay, well, from this Margulis lemma, there's a theorem of Jorgensen and Thurston, who did the manifold case. Dunbar and Meyerhoff extended to the orbifold case. The volumes of hyperbolic 3 overfolds form a well-ordered subset of R, of order type omega to the omega. So just like in the two-dimensional orbifold case. So Thurston posed the problem of finding the minimal volume hyperbolic 3 overfolds and manifolds, and more generally to identify the minimal volume orbifold of various types with, say, K cusps or arithmetic, coming from an arithmetic construction, or with first Bay number greater than or equal to K, things like this. Similar to the orbifold case, if I have a volume which is order type omega to the K, so it's a K-fold limit point, then it'll correspond to a manifold with K cusps, and the manifolds which are limiting to it, with volumes limiting to that volume, come from Dane filling on those cusps. So similar to the orbifold case. So Thurston proved that Dane filling decreases volume. So you can take this manifold with cusps, like the weighted link, and you can Dane fill the two cusps with various slopes, R. And as R goes to infinity, the volume of these manifolds which you've Dane filled will approach the volume of the cusp manifold. So these Margulis tubes, when you get the geodesic shorter and shorter, when you do a high Dane filling, this geodesic gets very short in the corresponding metric. So Thurston showed that you can perturb the metric on the cusp manifold to get a metric on the closed manifold. And as the geodesic length goes to 0, you can take a Gromov-Hausdorff limit, and it limits to this cusp with a torus on the manifold with a new cusp appearing. So this is somewhat analogous to the infinite cone point versus finite cone point in the two-dimensional orbifold case. So now I just want to talk about some known results on small volume orbifolds. Well, Meyerhoff showed that H3 mod PGL203 is a minimum volume non-compact orbifold. Well, when you add the reflection in as well, this non-compact Orientable orbifold. You take a reflection group in the tetrahedron to get the smallest one with non-orientable. And then PGL201, this is the second smallest non-compact orbifolds, which is shown by Colin Adams, and he found the next few smallest non-compact ones. The Giza King manifold is the smallest volume non-compact manifold. That was demonstrated by Adams. The smallest overfold with a limit volume, omega has volume something like 0.305, and Adams also found the next two limit points of three-dimensional overfolds. The figure 8 knot and its sibling are the minimum volume orientable cusp manifold. So they correspond to omega in the spectrum of volumes. This was shown by Sau and Meyerhoff in 98. The proof uses some rigorous computer checking, some rigorous computation. And then very recently, last year, Marshall and Martin identified the two smallest volume orientable overfolds. So one of them I showed before, it was a quotient of a tetrahedron. I've written down the orientable examples. They have an orientation reversing isometry, which gives you a non-orientable one that's even half that volume. There's another one that's not from a tetrahedral group, of volume 0.0408. So this is what's known about some small volume manifolds and orbifolds. Well, it turns out if you consider manifolds with boundary, that there's better estimates on the volume. So here's an example. You can make a hyperbolic metric on this. So I drill out these wormholes from this apple, and I get a manifold that has a hyperbolic metric on it that's made out of truncated tetrahedra. And you can do various packing arguments due to Brodsky that work much better when you work with geodesic planes than with spheres. So Brodsky proved that if you have a packing of spheres of radius r in Hn, the density is at most the density of, I take spheres of radius r inside a tetrahedron of edge length 2r, and I look at the density of that. That's the maximal density you can have of a packing of spheres in Hn. Well, it turns out in 2 dimensions you can have these triangles that realize these packing densities, but in 3 or more dimensions you don't have balls which achieve this density, which are invariant under a group of isometries. But if you let r go to infinity, the limit of a ball in hyperbolic space approaches a horoball. And it turns out in 3 dimensions you have this nice horoball packing, which does realize this optimal density. And there's a picture here. Well, this picture is not very good, but here's a packing by horoballs. This corresponds to the cusps in either the Giza King manifold or the figure 8 knot complement. This is invariant under PGL203, and because this achieves its maximal density, it's easier to prove some of these guys are minimal volume orbifolds with cusps. In the boundary case, when you have totally geodesic boundary, you can see some of these things. Well, I'll just put up a picture of this. This corresponds to a subgroup of the Whitehead link complement. This is this tetrahedron where I glued octahedron where I glued opposite edges. This is the picture that you see, and you can see these octahedra here. It's reflections in these 4 circles. This is lying in the boundary on the tabletop, and I have these geodesic planes sitting above them. And if I reflect through here, I get this pattern. All right, well, let's see. All right, I guess I'm already over time. Sorry about that. Let me just show one last slide about the volume spectrum, and I'll stop there.
You have until 10, so you're not over 10.
Oh, according to my watch. Well, okay. So here's the picture of the volume spectrum for 3 orbifolds. So we start out, so I explained some of these. So we have the smallest volume orbifolds have been identified by Marshall and Martin. The smallest non-compact ones were here and here by Meyerhoff and Adams. And Adams found the first limit volume. So these are orbifolds. And this corresponds to omega for orbifolds. Now for manifolds, for Orientable manifolds, the smallest volume is the Weeks-Medvedev-Fomenko manifold. This, just last month, was identified by Gabay, Meyerhoff, and Milley as the smallest volume Orientable manifold. So that involved a lot of computer work as well. This result depends on Perelman's proof of the geometrization conjecture, actually. And some of the other smallest volume manifolds, these are still unknown, whether these are the next two in the Orientable volume spectrum. The first limit volume was identified by Sal and Meyerhoff. I mentioned the figure 8 knot and its sibling with volume 2V naught. And what Gabay, Meyerhoff, and Milley did is they identified all the limit points up to volume 2.848. I think there's 10 of these. There's multiple manifolds associated with these volumes, but these are 5 volumes here with volume less than 2.848 of one cusp manifold. And then the smallest 2 cusp manifold, which corresponds to omega squared, is the Whitehead link in the -238 pretzel knot. So I proved that recently. Again, that depends on Perelman's work on geometrization. And I conjecture that omega cubed corresponds to this 3-chain link here, which has volume 5.33, but that's unknown. So this is sort of the picture of what the spectrum of volumes of hyperbolic 3 orbifolds is like. So now I'll stop there. Sorry to go over.
Any questions?
Offer a comment. So you
Yeah.
mentioned the figure 8 knot complement, and you credited that to Thurston and Riley. So there's a story there that went around in the 70s. I mean, that was a fundamental, groundbreaking example. Thurston worked on surfaces, 73, 4, maybe into 5, turned his attention to 3 manifolds, wondered about hyperbolic structures on them, and in particular knot complements, realized that he couldn't do it on the torus knot complement for certain algebraic reasons, but the figure 8 knot complement was a possibility. But realized if the figure 8 knot complement had a hyperbolic structure, then the limit of the fiber would be a space-filling curve of the 2-sphere. And that dissuaded him because somehow he didn't believe, I don't know whether he didn't know they existed, I can't believe that, of course, space-filling curves existed, but somehow he didn't think that would be a hyperbolic phenomenon. Anyway, he met Riley in Warwick one of the summers, 74, 5, 6, and Riley had worked out the exact representation, and Thurston was off and running after that became known to him. Anyway, it's an interesting story.
Yeah, some of these, it's fascinating that you can have these fiberings or these knot complements. The surfaces, I mean, as you say, there are these non-geometrically finite surfaces that whose limit, they limit on the boundary, the sphere at infinity, these piano curves, which come naturally from the topology. So they're very beautiful. I mean, I didn't have any pictures here, but Jorgensen also, the survey, I haven't been historically accurate and missed a lot of attributions, but Jorgensen also discovered these fibered examples. I think that was also influential on Thurston. Thurston at first, didn't believe these fibered examples could exist until the work of Riley and Jorgensen. Yeah.
Anything else? Let's thank Ian again.